So we are starting a new lesson in real numbers. So we'll first start with Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying the equation a is equal to b multiplied by q plus r, where r is less than b. So we'll just show some example to easily follow. Let us take example 9. 9 is equal to 2 multiplied by 4 plus 1. That's how the Euclid's division lemma says. Given a positive integers a and b, that's an example of 9 and 2. There exists the unique integers q and r, or you take it as remainder. Now remainder is always less than the divisor, satisfying the equation a is equal to bq plus r. So let us take the example of 10. What happens now? 2 multiplied by 5 plus 0. Now remainder is 0. Okay, we take the example of 11. Now 2 multiplied by 5 plus 1. So you can see each number can be expressed given a positive integers a and b. So this unique. The way of representing is if it is 10, the remainder is 0. If it is 11, the remainder is 1. So the way of expressing, if you take 12, it is 2 multiplied by 6 plus 1. Sorry, plus 0. So there's a unique way of defining each number as a product of two numbers plus remainder, where remainder is always less than the divisor. Or the same equation, see, you can write only this way, 5 multiplied by 2 plus 1. That is all. So we'll go some more theorems, go through and then come back. So the fundamental theorem for every composite number can be expressed or factorized as a product of prime, and this factorization is unique apart from the order in which the prime factor occurs. So, so we know what are all the prime numbers. So we'll just give some examples. What is prime number? Example, we'll start with 1. 2 is a prime number. 3 is a prime number. 4 is not a prime number. 5 and then 7. So 8, 9, 10, they are not prime numbers. 11, 13, so 14, 15, 16, they are not prime. Again 17, 8, 90, and goes on. So what the fundamental theorem? Each composite number can be expressed or factored as a product of prime, and the factorization of unique. Okay, let us take one example. Okay, take it as 100. So we express 100. 2 multiplied by 2 multiplied by 5, again multiplied by 5. Then this 2 2s are 4, 4 5s are 20, 20 5s are 100. It's a unique way. Now we can only change the order. We can say 2 multiplied by 5 multiplied by 2 multiplied by 5. The order can change, but the prime factors of every composite number is unique. The order may change, but this is unique. If you use these 2, 2 and again 5 and 5, the product you will get only 100. Okay, let us do the other way. You take the prime number 30 and prime number 2. So you get a composite number. This composite number you can express only by 2 multiplied by 13 or 13 multiplied by 2. The order may change, but would have only as a product of these two numbers. So this 26 is a composite. So these two are prime numbers. For every composite number can be expressed, or you can factorize a number, you can say, as a product of prime, and this factorization is unique. We'll go to the next theorem. So if P is a prime number and P divides A square, then P divides A, where A is a positive integer. So what is given? So P divides A square. Then P divides A, where A is a positive integer. So let us take what is A. A, see, let us take A is consists of A1, A2 or anything. So what is A square? The same prime factors multiplied by again A1 multiplied by A2 multiplied by A. So A is, no, P divides A square. So now, so these are all prime numbers. No. When P divides A square, P is one of the factors of A. Here, when factor is there, here if one factor is here also of other factor is available. So P is one of the factors of A. Therefore, P divides A. So therefore, P divides A. So next, so what is this say? Then if P is a prime number, if P divides A square, then P divides A, where A is a positive integer. So next, we'll go to next theorem about root irrational numbers. Root 2 is irrational. That is all. So let us go through the definition. What is rational number? What is rational number? Rational number possible to write in the form of P by Q. So where rational number can be expressed in terms of two integers P by Q of the form. So the proofs we will start. Let us assume to the contrary and prove that the contrary is wrong. Let us assume that root 2 is rational. If root 2 is rational, we can find integers, two integers r and s, such that root 2 is equal to r by s, both are integers. So what we do, the common factors we will divide. Root 2 will make the form of a by b, where a comma b are Co-prime. Co-prime means the only prime it contains prime numbers. Separate. There's no common prime between A and B. So common factors we can cancel it and make it in the form of A by B. So root 2 is equal to A by B. Or what do you say? Therefore, root 2 divided by B is equal to A. Square both sides. 2B square is equal to A square. Now, we are telling A and B are co-prime. So here we are telling it's co-prime. We are having separate. What about here? If you divide A square by B square, it is equal to 2. Now this 2 divides A square. So if we 2 divides A square, 2 divides A also. So we can write, so if 2 divides A square as per this, we can now divide by 2. 2B square equal to B. So therefore 2 divides A square. So as per the theorem above, if 2 divides A square, it divides A also. 2 divides A. So by theorem, 2 divides A also. A. So if 2 divides A, what we will write? We can write A equal to sum 2 multiplied by sum 6 for some integer. So again square both sides. Two divides A, 2 divides B square. If you say 2 divides B square, 2 divides B. So 2 is a common factor between A and B. So between A and B, 2 is a common factor. So which is contrary to the assumption. Therefore, root 2 is not a prime. So similarly, we can prove root 3 or root 3, root 5 is not a prime like that. The similar proof you just try to apply 2 times. It will be very clear. First, we have to assume on the contrary, but we will find that 2 is a common factor for both A and B. Therefore, our assumption is not correct. So we'll go to the next theorem. So if x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 to the power n multiplied by 5 to the power m, where n and m are non-negative integers, then x has a decimal expansion which terminates. So this theorem is useful in finding out whether the decimal expansion terminates or not. That's all. So let's say x is equal to p by q, rational number. Let us say it is 5 by 8. So the denominator, how we can write? It is 2 to 2 cube we can write. So if the denominator you can write 2 to, you need to find the power of 0, you can take it multiplied by 1, the denominator. Therefore, the decimal expansion terminates. Okay, let us take another example. It is 5 divided by 7. So, we don't have any factor up to the power of no factor, at the power of no, nothing is there. So, it's not terminating. So, let us, we will divide and check what is 5 by 8. So, equal to 0 0.68 or 48 to 20 to 8 or 15. 60 and 4 5 8 was 1, so it terminates. What about the other case? 5 by 7. Let us divide it 0 0.50 in 7 sevens are 49. Balance is 1 0 1 sevens are 7. Balance 3 4 sevens are 28. Balance 2 20 2 sevens are 14. Balance 6 60. 8 sevens are 56. Balance 4 40. 5 sevens are 35. 5 balance 50. So again it comes to 50. So this will repeat. Now if you see after this, it will again it will be 7 1 4 2 8 5. 7 1 4 2 8 5. It repeats itself. Please try to check this. So what the problem says, if x is equal to p by q be a rational number such that prime factorization of q is of the form 2 to the power n multiplied by 5 to the power m, where n and m are non-negative integers. It can be 0, non-negative integers. It can be 0 or any positive. Then x has a decimal expansion which terminates. This will be useful in solving where certain rational number of the form p by q is not ending. Thank you. With this, we come to the end of first chapter. Thank you for listening patiently. Now, these basic ideas and proofs of theorem we can only learn by repeating it number of times. And if there is any doubt, again, please go through the lessons again and repeat the lesson. Thank you.